Good morning. Thank you for watching my video. In this presentation, I'm going to present my joint work with my supervisor, Professor Andrea Matta. The work is about the automated generation of digital twins for manufacturing systems. I'm going to present a case study that we did in our lab to demonstrate the approach that we developed in the last year. This is a short overview of the contents of this presentation. I'm going to introduce the work with respect to the industrial relevance and present the problem. I'm going to frame the work with respect to the state of the art. And I'm going to give you a presentation about the methodology that we developed. Then I'm going to present the case study and give some ideas of the future developments and the results. This work is motivated by the fact that in the last years, manufacturing systems became very complex in response to pressures for cost reduction, a lot of pressures on the market demand towards a very high customization, and the complexity increased a lot. The result of the complexity is that even small events can cause a big impact on the manufacturing system performance. And so there is the need for online support tools that can help to plan and control the production. In the last years, at the same time, we had a tremendous development of technologies that can help the development of these tools, such as affordable data analytics and the possibility to collect information and gather an idea, a very clear idea of what is the system state at any time. So, I'm going to present where we started and what is the problem we wanted to solve. We have a manufacturing system that is very complex and is changing a long time. If we want to use an online support tool, we do need a simulation model that is aligned with the manufacturing system. In this figure, we see that if a manufacturing system changes a long time, the simulation model, which is typically developed at the design stage, does not follow the development of the system. If, in contrast, we could develop methods that generate models starting from the data that comes from the real system, then we could think of having a simulation model that is always aligned with the real system. And in this case, we can create digital models and use them at any time to support the production. In the literature, the idea of generating models starting from data of the system started with process mining approaches. Process mining is a technique that allows to generate models of systems starting from datasets. Nevertheless, the contributions in the literature are focused on other types of systems, and they do not address the needs of manufacturing systems. In particular, for example, they do not recognize finite capacity resources, and they have no relation with the performance estimation of the obtained model. Indeed, they concentrate on the understanding of the system rather than the capabilities of the final model that is generated. So this is an idea of the approach that we develop. We start from a manufacturing system. The manufacturing system generates a lot of data, which is collected in databases. From databases, we can collect several information that we are interested in. For example, the activity identifiers, part identifiers, and timestamps, which indicate the time that an activity has been done by a certain part. If we have a clear event log, we can generate a model with a model generation and tuning technique. A model can include several information regarding the system. For example, its configuration, the parameters of the system, such as the processing times, and the buffer sizes. But also more complex information, such as production policies and information about the resources. For example, the reliability models of the resources. Once we have a digital model, we can estimate the performance of the system with the digital model. And we can validate the digital model by comparing the performance with the real system performance. Here I'm going to give you an idea of how the model generation works. We start from our system, for example, in this case, a two-station system in which parts flow through the stations one after the other. So we have parts that flow, the first part flow from the first machine to the second one, and so on. The activities done by the parts are recorded in the event log. In the event log, we record three types of information. The timestamp at which a certain part has performed a certain activity. Starting from the event log, we can generate the traces, which are a list of activities performed by each part. From the traces, we can derive the activity relationships, and we can describe them in graph models. For example, this two nodes graph model indicates that station 2 always follows station 1 in this type of system. Once we have a graph model, we can enrich it with more information. For example, the parameters regarding some system properties. For example, the buffer capacity can be inferred if we observe that at least three parts have been queuing from station 1 to station 2. If we observe this, we can add a property to the arc that indicates the buffer capacity. Once we have generated a model, we can also understand that the model generation might not be enough. For instance, we can see that if we take the event log of a manufacturing system and we generate a model with the model generation technique, we might end up with a model that is overly complex. For example, in this figure, we can see that we have a three-station manufacturing system, and this generates a six-station graph model. This is because the event log records information also about the passage of parts through sensors. This type of information is redundant and does not add any capability of the model with respect, for example, to performance evaluation. So, we also developed approaches that can tune the model towards an appropriate level of detail. In the case study of this work, we are interested in understanding how the developed approach behaves in a real-time scenario. So we are interested in how the model structure is developed online, how the parameters are discovered online, such as buffer capacities and processing times. We might be also interested in other information, such as policies or reliability models, but we don't do this in this work. So how do we perform this analysis? We take a real system, a physical model, and we generate online the event log. Then we take a portion of the log and we perform model generation. For each portion of the log, a certain time of recording is considered. So we can understand how the model generation behaves depending on how much time has passed. In order to perform the analysis, we build a real manufacturing system model in a laboratory. We use Lego components to build a manufacturing system production line in scale. You can see in this video on the left that we can recreate with Lego components stations and conveyors that exchange parts represented by wooden discs. We can also recreate certain behaviors such as machine failures or blocking behavior due to the buffers that are full. So with very easy to build components and relatively inexpensive components such as Lego, we can build a manufacturing system line composed of a certain number of stations. For this work, we develop a model composed by 6 stations that are in sequence. Each station has an input buffer, and parts move around the system in a closed loop. Here we see the results of the case study. We start from the model structure. We can see that depending on the number of parts, the model structure is discovered. And we see that we need to wait a certain amount of time, around 100 seconds, to have the correct model structure, which is a graph model of 6 stations. From this figure, we understand that the initial transient determines the capability of discovering the correct model of the system. We also understand that the buffer capacities, that are the tags on the arcs, are not discovered in this time. So it means that we need to wait more time to understand the buffer capacities. Here is the results of buffer capacities discovered. We can see that almost all the buffer capacities are understood after a certain amount of time. But we need to wait at least 1000 seconds to see the correct buffer capacity. In this slide, we see how the processing time estimation works depending on which estimation method we use. We compare especially two estimators, kernel density estimation and empirical cumulative distribution function. We can see that if we wait not enough time, so only 1 day of production, we see that both estimations are not quite accurate because they cannot spot the right distribution. If we wait enough time, both estimation methods are okay, especially if we wait 9 days of production. If we have only 2 days of production, we see that with few data, the empirical estimation is better than the cumulative, than the kernel density estimation. In conclusion, we have developed a model generation approach, and we have seen how this is behaving in a real-time scenario. We are still limited by certain limitations. For example, we make the hypothesis of having only one part identifiers, and this limits the type of system that we can model. For example, we cannot model assembly or disassembly operations, in which multiple part identifiers might be present. Then, we also completely ignore certain type of information, and this results in less descriptive models. For example, we did not consider the reliability models of the stations. Finally, we also have manual pre-processing, which is still necessary to generate a model. In the future, we aim to test this approach on realistic datasets, perhaps also on real manufacturing systems. Then we want to extend the analysis to unexplored model elements. For example, we might include also the understanding of policies or the resource behaviors. Then we also want to understand how the approach behaves with very large logs, in which we might have the problem of converging several different information types in the same model. And also we might investigate simulation optimization applications, because if we generate graph models, we might also convert them in simulation optimization models. So thank you very much for your attention, and thank you for watching my video. I leave in this slide some of my personal contacts, and you can contact me if you have any question or doubts. And I look forward to meeting all of you in the conference. Thanks again.